we're going to cover kinetic molecular theory, which is the theory behind how gases work. So kinetic molecular theory says that the particles of the gas, which could either be atoms or molecules, are constantly moving. The attraction between the particles is negligible, and when the moving gas particles hit another gas particle or the container, they don't stick, but they bounce off each other and continue moving like billiard balls. If you remember at the beginning of this chapter, I mentioned how we think of these as billiard balls bouncing off of each other. There's a lot of empty space between the gas molecules, which we also mentioned before, and the average kinetic energy of the gas particles is directly proportional to the temperature in Kelvin. So as you raise the temperature, the average speed of the particles increases. Now it does note here, don't be fooled into thinking all the gas particles are moving at the same speed. It is an average speed, not the exact speed of every gas particle in your sample. Now, kinetic molecular theory can be used, all those assumptions I just talked about, can be used to explain the properties of gases. A good theory provides an explanation for how the world works. So, pressure can be explained because the gas molecules are constantly moving. They strike the sides of the container with a force, and because there are so many particles in the gas exerting those forces, that is a constant pressure. Remembering that the definition of pressure is force over area. The indefinite shape and indefinite volume can also be explained by kinetic molecular theory because the gas molecules have enough kinetic energy to overcome attractions. They fill whatever container they are in. They aren't limited by attractions to other molecules. And so since they fill the container, go and bounce off, they take the shape and the volume of the container that they are in. Compressibility can also be explained by kinetic molecular theory. There's a lot of unoccupied space, and so you can squeeze the gases closer together and compress them. The low density of gases is another property that can be explained by kinetic molecular theory. It has all this unoccupied space, which means there's not a lot of mass in the given volume, which leads to low density. Pressure is a result of the movement of gas molecules, which we talked about. So if we add more molecules, that means there are more molecules hitting the container at any one time, resulting in a higher pressure and also a higher density because there's more mass. So higher pressure leads to higher density. We can also talk about how to calculate the kinetic energy of a gas. Kinetic energy, you might remember from physics, is 1/2 mv squared. So the average kinetic energy is going to depend on the mass and the velocity. So gases in the same container have the same temperature, which means they have the same average kinetic energy. But if they have different masses, that means their velocities have to be different because same kinetic energy, different masses, the only other variable is the velocity. So lighter particles are going to have a faster velocity than more massive particles do. Here's a graph showing how various molecules, how their molecular velocity changes with the mass. So you can see hydrogen, lightweight, has a higher molecular velocity. It's also more spread out, so more molecules are farther away from the average. Then as you get bigger, you get a more crushed together distribution. Molecular velocities, as we saw in the last slide, have a distribution of speeds. That's a Boltzmann distribution. The way we calculate average velocity is called the root mean square method, which is going to be, you can get the average velocity, it's the square root of the sum of the squares of all the molecular velocities. So that's just how a Boltzmann distribution is calculated. Here it is, Boltzmann distribution. Notice the tail off here at the fast end. As your temperature increases, your average velocity is going to increase, and you flatten the curve, the distribution will spread out with more molecules having faster speeds, but some also have slower speeds, so your distribution spreads out as your temperature increases. How do gases travel in a container? They travel in a straight line until they collide with something else. The average distance a molecule travels is called the mean free path. And as you increase pressure, the mean free path decreases, which should make sense because as you increase pressure, there's less space for the particles to move around in, and so they're going to hit each other more often. Another characteristic of gas that we measure sometimes is diffusion, which is the process of a collection of molecules spreading out from a high concentration to a low concentration. So for instance, if I stood in a corner of a room and lit a match and had people at different distances from me, how quickly you could smell the sulfur smell from the match would be an example of diffusion. Effusion is the process by which a collection of molecules escapes through a small hole into a vacuum. So that's a more technical experiment that you could do in a lab. And the rate of diffusion and effusion is related to its root mean square average velocity. Or you can think of it, if gases are at the same temperature, the rate of gas movement is inversely proportional to the square root of its molecular mass. In other words, if gases are at the same temperature, a lighter gas is going to move faster, and how fast is inversely proportional to the square root of its molar mass. Here's a picture of effusion. So that's gases moving from an area of pressure into a vacuum. Notice there were no gas particles over here through a small hole. So the rate of effusion for gases at the same temperature can be related with Graham's law here. The rate of gas A over the rate of gas B is equal to the square root of the inverse of their molar masses. So if gas B is on the bottom, then it goes on the top, bottom, top. So calculate the molar mass of a gas that effuses at a rate 0.462 times of nitrogen. So we know if we have gas A over gas B, we're going to get the square root of molar mass B over molar mass A. Here we know that our rate is 0.462 over 1, so nitrogen here is our B, is equal to the square root of the molar mass of N2 is 28.02 grams per mole over our X in grams per mole. So if I take 0.462 and square it, that's going to be 28.02 over X. And then I can solve for my X, and I get 131 grams per mole. And here's that worked out in a PowerPoint slide.